Okay. Oh, it's the morning of a Sunday. Time to do the 2021 exam. I'll have a quick skim through the acknowledgements. And there's no articles I have to bring up. So hopefully this will be a nice, smooth exam. Okay. We're just ready to get started, I guess. Let's go 3, 2, and 1. Which of the following statements is or are true for redox reactions? Transfer of electrons, yes. That's not true. Oxidation is the gain. Reduction is loss, no. And that is true, so D. Oxidation is loss. Chlorine is bubbled for several minutes through a sample of pent 1E. In order, the following identifies the type of reaction that occurs and the color of the solution after the reaction is complete. Assuming the chlorine gas is limiting. So this is an addition reaction. And since it's reacting with an alkene, it's gonna decolor, so be colorless. Consider the acids in the following table. Which of the following identifies the strongest acid and classifies it accordingly? So the strongest acid is gonna have the biggest K value, so it's gonna be the tri whatever. And you can only get rid of that one acid. Make sure that's right. Looks correct. Which of the following characteristics influence how a particular polymer might be used? The amount of cross-linking between hydrogen atoms. Nope. Cross-linking is between sulfur. Length of the carbon chains. Sure. Functional groups present. Yeah. Melting point of the polymer. So we'll say 2, 3, and 4. 4 is definitely, 1 is definitely not. 2 and 3, no, because 4 is also true. Nylon 46 is a polymer that can withstand very large forces without breaking. Its structural formula is shown below. The intermolecular forces contributing to the most of the strength of nylon 46. You can probably say a hydrogen bonding. Most of the strength. Would it be hydrogen bonding or will it be dispersion forces? I think I'm going to say this, but hydrogen bonding. So can hydrogen, because we have this polar carbonyl group, and then we have the amide group. Going down, which of the following is least likely to be a characteristic of a process classified as green chemistry? It's energy intensive because we want to try and reduce energy. Which of the following structures represent glycine in acidic conditions? So we're going to have pH down, so then we're going to have the positive what's it considered ion, so it's going to be this one because we need the NH3, which we can see there. Which of the following equations demonstrates the Arrhenius model of acids and bases? So it's going to be something that dissociates to make H plus ions. So that is one. That is not one. This is another one, and that is not one because that's donating, so it's 1 and 3 only. The net ionic equation for the predominant hydrolysis reaction occurring in 1 mole of potassium hydrogen sulfate solution is potassium net ionic. So this, get rid of that one, get rid of this one because the K aqueous ions are present in both. And then we have HSO4, which is gonna become, so H2SO4 is an acid, and I'll release both. A strong acid is gonna be a weak base. It's probably gonna be this one because it donates the hydronium away, or the hydrogen away. Which of the following identifies the recharging ability of a particular electrochemical and provides an appropriate example? So it is secondary cells that are rechargeable. Lead acid accumulated. Okay, which of the following shows an alpha amino acid? H2 think it's only 3. Because you need to have the NH2 and then the COH, and then you need to have another carbon coming off of it with only 1 CH. And then like these ones, they have 2 CHs, 2 CH, and then this one doesn't have. Oh wait. Okay, so it's definitely not 4, and it's definitely not 2, because these are coming off not the same carbon. Is it 1? Is there a 3 only? There's no 3 only, so I guess one of those are 1. So we'll say 1 and 3 only. Maybe we can have oh wait, yeah, because that's just alanine, isn't it? Or glycine. Yeah, glycine, CH2. Yes, okay. So 1 and 3 only. Question 12 is the following electrical chemical which contains a light bulb. Which of the following combination of the aqueous will result in the possibility of the globe glowing? So let's see. So we're gonna have nickel aqueous. Just gonna do my right hand rule or my clockwise rule. Nickel aqueous, and then silver. It's definitely no. Silver. Because I don't have silver. Graphite. So let's see. Nickel solid. Aqueous. G plus. Okay, so this may be. Wait, silver electrode. No, that won't work then. Yeah, that's a bit odd. But nickel electrode with silver like that. I don't think that will work. So let's see, nickel with nickel solid, aqueous, and then the silver gets reduced, Ag. That's how it works. The salt bridge provides the ions that are oxidized or reduced. That's no. Transfer facilitating electrons and ions. It doesn't transfer the electrons. No, provides ion facility. Let's complete the electrical circuit. Transfer of electrons and ions. It doesn't provide ions. Maintains the overall electrical and pH neutrality of the cell. Facilitates ion movement between cells, complete electrical circuit. I think this is the better option because it doesn't necessarily maintain pH neutrality and it's not by the transfer of electrons. But this I'm not so sure about providing ions, but I think the best answer there is going to be D. Consider the following pH values for the range of substances. Based on the pH, which is true of the following statements about the concentration of ion. Okay, it is 10,000 times greater in seawater than in bathroom cleaner. So where is seawater? Is at 8. Bathroom cleaner is at 11. So that's 10. 100, 1,000, so this is true. It's not twice, not. Okay, let's see. Hair straightener and milk. So hair straightener and milk. No, it's 1,000 times. That's 1,000,000 times less. Okay. Which of the following processes does not contribute to the building of weaker seashells through ocean acidification? Does not. Obviously this does. This does. This does. Contribute to the building of weak seashells through ocean acidification. Does not contribute to the building of. Oh wait, I have to set my timer. So give me a second. Okay, back. Let's continue. Okay, I think A and B definitely aren't because they are just they're showing ocean acidification. So it's between these two. Ocean acidification. I feel like this is a better answer for why it is, because it clearly shows acidification and the seashells being like destroyed or whatever. So I think not is going to be C. Carbonic acid. Two isomeric forms of a saturated hydrocarbon contain different types of atoms, same structural formula, same molecular formula, reacted vigorously. They have the same molecular formula. A chemist performed a series of titrations and published the results in a scientific journal. From the point of view of the chemist, the titration data is primary because he did it himself. An example of a random error in the titration is the gas bubble in the breath tap that comes out during a titration. Maybe B. That's systematic. And that's not. In which of the following reactions will there be no visible reaction at 25 degrees Celsius? Let's see. Solid iron strip is placed in a solution. What's that? Of 25. 1 molar copper 2 sulfate. So I need solid Fe and then copper sulfate. Copper. So that will be. It's not this one. Bromine water and 2-methyl, 2-dimethyl-butene are shaken together. That one's fine. That's not that one. Chlorine gas is bubbled through a solution of 1 mole of potassium iodide. So CO2 gas and potassium iodide. So this would be one. Some dichromate and acetic acid. Yeah, it'll be this one. Because the acetic acid is already the most oxidized it can be. So it was not going to oxidize further, so the potassium dichromate is going to stay as the certain color. Consider the following reversible reaction. Which of the following statements describes the relative concentration of reactants and products in the system? When equilibrium is established in a closed vessel, the concentration of reactants and products will be equal. Not true. There will be a greater concentration of products than reactants. Yes. Reactant concentration will be greater than that because it's product over reactants. Concentration will be double the concentration of CO2. No. Identify conjugate acid-base pair of devices. So they need to differ by only 1 hydrogen. So it's going to be this guy. In any electrolytic cell used for plating objects of gold, the object to be plated is the anode, that's the cathode. There must be salt bridge connecting anode and cathode. Nope, because that's in galvanic. The reaction is spontaneous, that is not true. A reaction of a piece of pure gold uses a positively charged electrode. Positively charged electrode in electrolytic would be the anode, and that's supposed to be oxidized, so yes. The equilibrium content of a system depends on the concentration of reactants and products. Question 24 refers to the following information. Equal moles of nitrogen dioxide gas and nitrogen tetroxide gas are sealed inside 1/2 of 2-chamber reactor as shown below. And then it's 25, after which the following inside. More N2 gas is added to chamber 1. What observations will be made about the color of the gas mixture and its temperature after a new equilibrium is established? So this is going to increase. So we're going to make more reddish brown. So that's going to increase. So we're going to go to the left, so that's going to increase. And since it's going to be more reddish brown, this is colorless, so it doesn't affect the color. So we're going to get a darker brown. And we're going to the left, so that's going to absorb temperature. So the temperature, absorb energy. So it's going to be lower temperature. The valve between the chambers open, allowing the gas mixture in chamber 1 to fill both chambers. Which statement describes the initial and final observations of the gas as a new equilibrium is established? So when the tap is open, it's going to be a paler brown because this will decrease and this will decrease. But the volume will increase and my pressure decrease and my concentration decrease. So it's going to be paler brown. And observations as equilibrium is re-established. We want to increase the pressure, so we're going to go to the left, so it's going to become more brown. So become darker. So paler brown became darker. 25. Okay, short answer time. 8 questions. Okay, issue following for each. State why the name given by the student is incorrect and rename it using the IUPAC nomenclature. So carbon containing carbonyl group. Maybe I'll say carbonyl group should be named or numbered with the smallest possible number, as it is the most significant functional group. It's the most significant functional group. So the proper IUPAC name is going to be 2-pentan, so pentantuone. So 1 amino propanone. Oh, this is a primary amide. This is an amide. Not a amino ketone. What's an amine? And a ketone. So this would just be propanamide. Propanamide. Circle an error in each structural formula and state the reason why it is an error. How are you going to circle this? Yeah, circle like that. Carbon contains 5 bonds, which is possible. Incorrect. I'll say incorrect. Its maximum is only 4. I'll say central carbon in circle. Student structural formula. This oxygen shouldn't be by itself. Circle this. The oxygen should have a hydrogen bonded to it, because this could be the student trying to draw a ketone, I mean an aldehyde, or it's trying to draw an alcohol. Double bond to the carbon. And then remove one of the hydrogen atoms. I'll say this is an alcohol, or it would make an alcohol, and this would be an aldehyde. I think. Yeah, oxygens should have a hydrogen bonded to it, or have a double bond to the carbon. I think that's the error. Okay, moving on. How many pages are there? Jesus, oh god. Yikes. Oh, only 38 pages. Nice chill exam. Okay, alcohols exhibit a variety of different chemical properties. For example, some alcohols react with acidified permanganate ions, while others do not. The alcohols in the following table are heated with excess acidified potassium permanganate, and all organic products formed during this process. If there is no reaction, indicate by writing no reaction. So 2-methyl-pentanol, pentan-2-ol. So 2, I'm going to have an OH and then a methyl group, so that's going to be no reaction. Pentan-1-ol, we're going to get pentanal. We're going to have the aldehyde, and then we're also going to have pentanoic acid. For pentan-2-ol, that's a secondary alcohol, so we're only going to get pentan-2-O. Right, advanced overall ionic equation showing the formation of one of the organic compounds named in part A. Only the alcohols listed in the table and acidified permanganate conversion can be used. Show your working. Net ionic equation showing the formation of one. Okay, so let's go pentan-1-ol. Showing the formation of one of the organic compounds. So then this will be CH3, CH2, 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 CH2OH, aqueous. We're gonna have a water, and then this is gonna form CH3, CH2, 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 Actually, let's do it forming pentan Al, so it's easier. So we'll get rid of this water, because this is just going to make CHO, aqueous, and then we're going to have 2 hydrogens left over, so we're going to need to balance that with 2 electrons. And then the reduction is MnO4 permanganate, so MnO4 minus aqueous plus 8H plus aqueous plus 5 electrons to form Mn2 plus aqueous plus 4H2O liquid. Okay, so then let me deal with my hydrogens. On the left hand side, I'm going to have to multiply this by 2, so I'm going to have 16, and then the top equation I have to multiply by 5, so I'm going to have 10. So I'm going to have 6 on the right, and then for my water, I'm going to have none on my left, and then 8 on my right. Let's make sure this is correct. Yep. And then redox. Action. For redox reaction, I'm going to have 5 CH3, CH2, 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 CH2OH, aqueous plus 2 MnO4 minus. I'll deal with the ions in a second, plus 6H plus aqueous. It's going to form 5 CH3, CH2, 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 CHO, plus 2 aqueous, plus 2 Mn2 plus aqueous, plus 8H2O liquid. So then full ionic. The only ions I can see are the Mn plus. Yeah, it's going to be the Mn. So get rid of those, and get rid of those. So then I'm going to have 5CH3, CH2, 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 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 aqueous plus 2O4 3 minus aqueous plus 6H plus aqueous. This is going to form my aldehyde, so 5CH3, CH2, 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 CHO, aqueous, plus 8 waters, H2O, liquid. So let's see, I have 13 oxygens, which is correct. I have 3 plus 2 plus 2 plus 2 plus 2 plus 1 is 12. 5, 7, 9, 11, 12 times 5 plus 6. I have 66 hydrogens. So 3 plus 2 is 5, 7, 9, 10. It's 5 plus 16 hydrogens. Yes, it's all good. Okay, moving on. The same type of reaction occurs with alcohols and mixed with acidified potassium dichromate solution. So this is an oxidation. State how the reaction observations are different when limited acidified potassium dichromate is used instead of limited acidified potassium permanganate. Dichromate will have orange solution turning gray. Orange solution turns green. Because of the chromium ions, turns deep green. And then the permanganate We have purple solution, turns, and then Mn2 plus turns pale pink. There we go. Benzenoic acid is a weak acid. Its structural formula is shown below. Range of uses, including the manufacture of dyes, perfumes, and insect repellents. Contains the acid content of these products can be determined by titration of sodium hydroxide. The salt produced in the titration is sodium benzenoate. The following graph show the typical acid base for that. Which of these indicators listed best suited for the titration? With reference to the above titration curve, explain your choice. So let's say equivalence point around pH of 9, because it's about there. So it's probably best to use cresophelline. 0.2 to 9.8. So we'll say creso pH. I think I spelled phthalene, right? Yep. From titration curve, equivalence point at equivalent point roughly equal to 9. Therefore, pH range of indicator must contain or be very near pH equals 9. Only cresophelline contains pH of 9. pH, THLEIN contains pH equal 9 in its range. Therefore, creso. Therefore, best indicator. Therefore, most suitable. Okay. Buffering is observed during this titration. Circle the region on the titration curve to show where the buffering occurs. So when you add volumes of A, so it's going to be after the titration, because then you have this negative ion, and then that can buffer with this guy. So we'll say there. Define the term buffering and explain why occurs during this titration in the region you circle in PII. Include an equation to support your explanation. Buffering is the ability for a solution to prevent significant changes in pH as small volumes of acid/base are added. And then it is, and then they are formed from weak acid and weak conjugate base. They are formed from weak acid and weak conjugate base. Conjugate base pairs. Wait a minute. No, I don't think it'll be there. Volume of NaOH added. Okay, it's only moving slowly up here because it's already super basic. So I don't think that's why. I think it would be in this first region. Because here you would have some amount of this guy and the negative, because over here you're only going to have this, which is the negative ion, and obviously that can't form a buffer, so it would be this region. So at region circled, there is both benzenoic acid, and sodium benzoate, benzenoate. The buffer is formed between the benzenoic acid and benzenoate, an ion. Benzenoate ion. Sodium benzoate from sodium benzoate. It works by neutralizing the pH. Neutralizing OH minus by reacting it with the benzenoic acid. Less excess OH minus, therefore minimal change in pH. Neutralizing added. OH. Okay, so now I have to do the full equation. So let's see, it's 1, 2, 3, 4, 5, 6, 7 carbons. And then 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4, 5, 6, and 2 oxygens. C7H6O2. So we'll do C6H5 COOH aqueous plus OH minus aqueous. This is going to form a reaction buffer, and it's going to form C6 H5 COO minus aqueous plus H2O liquid. So 1, 2, 3, 1, 2, 3, 6, 1, 2, 3, 4, 5 COO. Yep. Minimal change, so it's reacting with the OH. Yep. Okay. Water can self-ionize, as shown in the following equation. Reaction, equilibrium, and pH of water are both affected by changes in temperature. The data in the following table shows how changing the temperature affects the pH of pure water. Show how the tabulated data in the Chatelier's principle can be deduced over the self-ionization is exothermic and endothermic. Calculations are not required. Then pH, we'll do this. So pH is equal to negative log 10 of H3O plus ions. So we'll say from table, as my temperature increase, what we see is that pH will decrease, therefore H3O plus must be increasing, hence forward reaction, hence H plus aqueous is being formed, therefore above reaction favors forward direction. Wait. No, yes, okay. pH does decrease. I thought for a second I was reading this backwards. So, form the Chatelier's principle. Yeah, I'll write the full thing first. The Chatelier's principle. The Chatelier. That sounds like the Overwatch map. Like Le Chatelier or something like that. I'll say here LCP. As temperature increase, endothermic reaction favored. To oppose the change, or partially oppose change, by absorbing energy to decrease temp. As forward reaction favored, when temp decrease or temp increase, forward reaction must be endothermic, and therefore we can say self-ionization of water is endothermic. Self-ionization of water is endothermic. Calculate the H of pure water 100 degrees, here and kW is equal to that. Okay, so then kW is equal to this, and then OH minus, and it says in pure water, my hydronium concentration equals my OH concentration regardless of temperature. So then therefore 5.13 times 10 to the negative 15 is equal to this squared. I remember I made a mistake last time because I had a calculator error. Therefore, I can just do H plus, H minus, H plus is equal to that. H plus squared, so then we know that H plus will be equal to the square root of this. 15 plus square root 5.13 times 10 to the negative 15. It's going to be 7.16. 366 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8. Therefore, my concentration of OH minus is also equal to 7.16. So that's small, so we can have bigger. So let's see, 7.16 times 10 to the negative 8 squared gives me 5.13. Nice. 10 to the negative 15. Fuel cells, such as the one shown in the diagram, use gaseous hydrogen and oxygen to produce electricity. Complete both diagram by adding labels or arrows to show that anode, cathode, direction of electron flow, and direction of hydrogen ion flow. So hydrogen gas in is going to get oxidized, and then this is going to get reduced. But oxygen is usually, surprisingly, the oxidant. That's an easy way to remember it. And then whatever hydrocarbon or hydrogen or other gas you put in is going to be the fuel, and the fuel gets oxidized. So that's going to become like that. So the hydrogen ions are going to move towards the O2 gas. And then O2 plus H is going to make water, yeah. So it's getting reduced. So this is cathode. And then since this is being oxidized, this will be the anode. And then no matter what cell you have, electrons flow anode to cathode. Because at anode, they're losing electrons. They want to get rid of them. And then at the cathode, they want to gain the electrons, so then they can do the reduction process. Okay, right, balance half equation for the oxidation and reduction equations, and the equation for the overall reaction occurring in this fuel cell. So oxidation equation is just going to be H2 gas, which is going to make your hydrogen ions. So 2H plus aqueous, and then just balance that with electrons. And here we're going to have oxygen gas, plus we're going to have 4H plus, because we're going to have to make 2 waters, and each water only has 1 oxygen. And 4 electrons. This looks like a C, electrons. And then this is just going to make 2 waters. I bet you the next question is going to be, why is this a better one than, never mind, okay, it's not. Just a second, I've seen something very similar to that, okay. Overall equation. So let's just work on our H pluses. I find this to be really useful, just because I always seem to mess up my H plus and H2O in past exams. So let's see, I'm going to have 4 on the left and 4 on the right. So I'm not going to have any. And then my H2O, I'm going to have none on my left and 2 on my right. Okay, so it's going to be 2H2 gas plus O2 gas. And this is just going to form 2H2O liquid. Does that balance out? Yes, it does. This fuel cell typically produces 0.7, which is significantly less than the predicted value of 1.23. State 2 specific conditions of the cell that will account for this observation. Temperature not at 25 degrees Celsius. Uh-oh, what's the other one? Is it that my pressure isn't at 100 kilopascals? And then pressure not at oh wait, it just says state 2 specific conditions. 100 kilopascals, I think. Which uses sulfuric as the electrolyte. The hydrogen and oxygen circulate at very high pressures over porous nickel-platinum electrodes. Operating ranges range from 25 to 90 degrees Celsius. So yeah, my pressures are different at 90 degrees Celsius. High pressures. Say here, not at 100 pascals. High pressures. Very high. $31. Corrosion of iron is an electrochemical process that results in the formation of reddish-brown solid commonly known as rust. which is FeO3H2OS. Iron objects exposed to rainwater corrode relatively quickly. Iron corrosion occurs in two stages. During the first stage, the electrochemical cell is established on the iron surface with electron transfer and Fe2 ion transfer occurring. This can be seen in the following diagram. And above, electrochemical cell state symbols are not required. Okay, so oxidation is just going to be the Fe to Fe2 plus 2 electrons. I can't remember my E's today. Fe2 plus 2 electrons. And then electron transfer is water with the H2. So it's going to be O2 gas plus 4H plus aqueous, because we need that. And the pH is low, which means we can assume acidic conditions. So yep, I can have H pluses and then 4E minus, not aqueous, sorry. Oh, I don't actually need these. There we go. And then this will make 2H2O liquid. Because you can see that it produces H2O there. And then, oh, I don't need that liquid. Redox equation. So this one, I don't have any H pluses or H2Os on both equations, so it's going to be relatively simple. It's going to be 2Fe plus O2 plus 4H plus. It's going to make 2Fe2 plus 2H2O. During the second stage of this ion corrosion, the newly formed Fe2 plus ions migrate away from the ion surface and react with water and dissolve oxygen to form rust. As the equation is shown below, use oxidation numbers to show that the reaction is a redox reaction. So here the oxygen gas goes from -1 to -2, and the Fe2 plus goes from +2. So let's do the first one. So oxygen oxidation number. Oxidation number. It goes from -2 in O2 gas to, oh sorry, it goes from 0 to -2 in the Fe2 H2O. Actually, do I need to specify which? I don't think I need to specify which oxidation. I think I just need to go to -2. I say therefore reduced, and then Fe oxidation number. It goes from +2, so there's going to be -6 in total, so that's going to be +3. So it goes from +2 to +3, therefore oxidized. Therefore, an atom is oxidized. And another is reduced, therefore redox. Okay, a corrosion chemist who found that most equipment containing iron shows different methods, including use of sacrificial anode. So sacrificial anode is a more reactive metal that is contacting the iron or attached by wires. Or attached by some circuit that will get preferentially oxidized in place of the iron, preventing corrosion/rusting. Preventing corrosion of iron. Making iron the cathode. I think that should be enough of an explanation. Preferentially oxidize and place the iron for any corrosion of iron. Okay, state the name of a metal that can be used. Justify standard reduction potential. Okay. So I just need anything lower than Fe. So I'll say maybe magnesium. Magnesium metal. Then E0 of Fe2 plus Fe is negative 0.44. And then E0 of Mg2 plus Mg is negative 2.36 volts. Therefore, Mg more reactive will get preferentially oxidized. Ammonia. Yes, a nice equilibrium constant equation. Manufactured industrially by the Haber process, the reaction equation being that at 400 degrees Celsius, the equilibrium constant of this reaction is equal to that, and the activation of energy is equal to that. Okay, so Kc is going to be NH3 2 all over N2 and then H2 power 3. As usual, I can label the axis product. So the activation energy of the forward is 400 kilojoules. So I need to go up to 600. Maybe about there. And then I need to do, and then it releases 92 kilojoules. So I need to go to about 110. Get the ruler out for this. That was pretty good. So this is my 100 line. So I need to go just a little bit above that. So something like that. So now I can see that this is my delta E, or delta H, sorry. H is equal to negative 92 kilojoules per mole. And then here's my activation energy. So activation energy, I'm going to say this is EA equal to 400 kilojoules per mole. What I say, I need the axes. So this can be my enthalpy. And this would be in kilojoules per mole. And then axis product, so down here is going to be progression of reaction. And then I'm going to need my products, which is going to be just NH3. 2 NH3 gaseous. Okay. How many marks are in this again? 35 plus 76 plus 90. 191. Windows section 3 start. It's only 37 pages. Section 3 starts at page 23. Oh, so nearly there. Gonna have 2 hours, Jesus. Some hydrogen, nitrogen, and ammonium was sealed in a reaction vessel, and the concentrations were monitored for a period of time as shown in the following graph. A change was made to the reaction system at time x. Identify this change and use collision theory to explain the shapes of the curves in the region x to y. So at time x, ammonia was removed from the system. System instantaneous decrease in ammonia concentration following that NH3 so then as NH3 decreases, N2 and H2 as NH3 decrease. And then what's collision theory? Yeah, NH3 decrease. Frequency of product collisions decrease. Therefore, reverse reaction rate RR decrease, and then forward reaction rate not affected, therefore forward reaction favored. Hence, product increase and reactants will decrease. Any gradients? Oh, I mean, I should say concentrations. I'll say it's like a concentration of species indicate gradient of reaction rate or forward / reverse reaction. Okay, and then so the products will increase and reactants will decrease. And let's say as reaction progresses, and the concentration of products increase, concentration of reactants decrease. Reverse reaction rate increase and forward reaction rate decrease. As respective frequency of collisions therefore net forward reaction maybe I should say here that hydrogen gas has 3 times the change. Similarly, NH3 is twice the change. The opposite direction due to stoichiometric ratios. Frequency of collisions decrease and increase. For formation. Products. Slows down. Seen in the gradients getting flatter. This occurs until equilibrium is reestablished. Reestablished. When reaction rate of forward equals reaction rate of reverse. The then system is in dynamic equilibrium. So back. So concentration of products and concentration of reactants. Remain constant. Concentration gradient in the file. The temperature of the system was increased at time y, shown on the graph how this affected the concentrations of hydrogen, nitrogen, and ammonium as the system returned to equilibrium. So temperature increased. Temperature increased, so we're gonna go to the left because we're gonna want to absorb. So we want this increase, so we're gonna go to the left. To absorb it, so let's say N2 increased by some amount. System returns to equilibrium. Let's just draw some arbitrary line where they reach equilibrium. Let's say like here, here, blah 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 blah. Let's say we want them to reach equilibrium there. So let's say the N2 goes up by 2. So then the hydrogen needs to go up by 6 of these lines. There. There are 2 lines. So there. And then the ammonium needs to drop by 4 of these lines. So there. That. I'm just doing this on my iPad in this manner because if I had an actual piece of paper, it'd be much easier to draw in. But the things you gotta do to eyeball. And then this is ammonia decrease. Like that. And now I can get rid of these lines. And it'll be just like that. Nice. Nitrogen and hydrogen will increase, and nitrogen and ammonium will decrease. Okay. Ethanol that dissolves readily in water while decanool has very limited solubility. Explain the able layer diagrams where ethanol is able to dissolve and decanol is not. Let's do the diagrams first. So let's say this is my CH2. right here, just positive, negative, positive, negative. These can be my hydrogen bonds. Overcame H2O hydrogen bonds. And then for my decking 1O, so then CH, so C, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, OH. And then we'll say that 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 3, 6, 9, 10. I just didn't draw a spaced out, I guess. Let's see. 8, 9, 10. And this can be hydrogen bonding or dispersion forces. Negative. Wait, no. Okay. Positive. H bonding. Ethanol. Okay, let's start with water. Let's start with water first. Water is a polar solvent. With dispersion forces, dipole, and primarily dipole, but primarily hydrogen bonding between its molecules. If a solute is to dissolve in water, the sum of intermolecular forces must overcome the H2O INF and solute intermolecular forces. Ethanol is primarily hydrogen bonding. I'll say along with dipole. Between itself. Due to its polar nature. Therefore, ethanol, we'll say attractive intermolecular forces between ethanol let's see here, primarily H bonding between ethanol and water is sufficient to overcome ethanol intermolecular forces and water IMF, therefore dissolves readily. Ethanol. We should say it releases enough energy to overcome that. Dissolves readily. Decan 1O. Hence dipole or is largely nonpolar. Does exhibit H bonding and dipole. Is they are overshadowed by the much more powerful dispersion forces between itself. And it's large hydrocarbon tail as such. Attempting to form as such the attractive IMF, so H bonding dipole and dispersion between Decan 1O and water does not release enough energy to sufficiently overcome the solid Decan 1O between itself. Therefore, does not dissolve readily. Primarily H bonding, dipole, and dispersion. Largely polar nature. It's largely non-polar. Stronger. Okay, I think that's pretty good. Oh my god, I hate this. No. No, when's the empirical formula question? Where's the empirical formula question? Oh my god. Yikes. Okay, I don't want to do this. ASP. Let's go, let's get this done. Aspartic acid, oh my god. So a section. So it's a section, so I need to not terminate my bonds or the links. Draw the full structural formula. Okay, fine, whatever. So H. C, that will double bond to O, and that become an N. Aspartic acid, so C, I'm gonna have a H and a H. I'm gonna have a C, double bond OH. Wait, no. Okay, let me think about this. The carboxylic acid is bigger between carboxylic acid and an alcohol or an amine. So carboxylic acid loses the whole OH. Like that. So then N. And then I have another C and I have another H. PHE. What's PHE? Phenylalanine. Okay, let's just do this first. I'm gonna have H, I'm gonna have H, and then there's a benzene ring. So boom, boom, oh god. Boom, 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 boom. That. They're not even connected. Jesus Christ. What am I drawing? Connect the. Oh god. That. Benzene ring. HC. And then this is my amide bond. Polypeptide. Leucine. Oh God's sake. CH. C double bond to O. And C I have a H and I have a H. And then I have a C. And then a single H. And then C H. 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 And then C H. 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 And then the next, final one, CHCOO. Nope, I'm gonna finish that because it loses the full OH group. So I do like that. And then ARG. Oh my god, you're actually kidding me. They're literally just trolling. They're literally just trolling, making me draw this. See, I don't get why they have these questions. All it is copy and paste. This is like, can you read a table? I swear they just put these in to slow people down. I'm gonna say that's my H, C, N to H, and then another N, H, H. That's literally terrible. God's sake. Okay, whatever. The amino acid in keratin forms alpha helixes, with two alpha helices twisting around each other to form what's called a coiled coil that's held together by disulfide bridges. Circle the primary recognizes an alpha helix is secondary. What does the presence indicate that the primary structure of keratin contains cysteine? Because cysteine is the only, what do you call it, alpha amino acid that can disulfide bridge. Synthetic fingernails are a popular fashion accessory. They are made in industrial laboratories for polymers, and monomer that can be used to make polymer suitable for synthetic is shown. So the circled functional group in this monomer is an ester. Give the IUPAC name for the alcohol needed to make this monomer. So the alcohol is just going to be this. Sorry, it's here for H at the end, so that's going to be ethanol. Ethanol. And then, yeah, because that's the carboxylate. Okay, draw 3 repeating units of the polymer made from this monomer. You're actually joking. Okay, so it's going to be C, double bond C. This is the monomer, so H, and then there's a H, and I think it was H, and then it was CH3. And down here became, there's an ugly C. It was C, O, 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 and then CH2, CH3. Okay, so that's just the monomer. So then it's going to be 1, 2, 3, 4, 5, 6, and you're going to continue that off. H, 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 H. Again, these are just like, they're just to slow you down in the exam. These are not skillful questions. CO, CH2, CH3, CO, CH2, CH3. And then this is CO, CH2, CH3. Okay. The protein which makes natural fingernails, keratin, is also a polymer. Which type of polymerization does keratin 86, and what type produces synthetic fingernails? So protein. Polymerization. So this is just a condensation because it has the reactive functional groups, because it's a polypeptide, and synthetic fingernail polymer, it's just going to be addition because you're breaking that double bond. State 2 differences between the polymerization reactions identified in part G. So condensation, reactions produce H2OL, while addition does not. Produce any extra species. And condensation. Forming and linking between two, or requires two monomers. Well, addition, what is addition? Code. So condensation requires two or more monomers. With reactive functional groups. And then you could say that addition can be achieved with a single monomer requires monomers with I guess you could do condensation reactions between ones if they have an alcohol group and the carboxylic acid group on the side. And I'll just say requires monomers with reactive functional groups. Achieved with monomers. And I'll say addition requires an alkene C double bond in the monomers. Monomer, and I'll put a bracket S. With reactive functional groups, then for addition you'll need alkene. Okay. Smoking is a hazardous to a person's health, and one option to help quit smoking is the use of nicotine pouches. These patches, when placed on the skin, release small amounts of nicotine with the aim of reducing cigarette craving. The nicotine content of these patches can be determined by titration. The titrating solution is prepared by mixing perchloric acid with glacial acetic acid, resulting in the formation of equilibrium. The species that reacts with nicotine during the titration is that glacial means that the acetic acid does not contain any water. The perchloric acetate solution must be standardized before use, and this can be done by titrating of a solution made from a primary standard. Other than possessing relatively high molar mass, take two characteristics required of a substance for it to be used as a primary standard. So just a substance. So it needs to have a known, say, readily available in a pure form, in a known pure form. I would say a pure form. Pure form, a known percentage purity. Another one, it must be I'm gonna say stable when being stored. Easily stored. Does not react with moisture or CO2 from our atmosphere. So readily available in a pure form and can be easily stored. Does not react with moisture or CO2 from the atmosphere. And I guess known molecular formula. Easily stored in a stable state. Okay. Nicotine comes in dose packages 7, 14, and 21. A manufacturing error produced a batch of unlabeled box of patches. The chemist was given the task of identifying the dose size so that the boxes could be accurately labeled and sold. The boxes from nicotine was made to a total of 100 using a suitable solvent. Aliquots of the resulting solution were then titrated with standardized perchloric acetate solution requiring an average of 15.11 to reach the endpoint. So task mixing 100 milliliters of the, so this would be a volumetric flask. Measuring 20 millialiquots of the nicotine content, so this would be a pipette. And then adding to the, this would be a burette. Okay, using the chemist's titration data, identify the nicotine in the unlabeled boxes. The molecular formula of nicotine is that, and the titration equation is that. Okay, so it reacts with 2. So let's see. number of CH3COOH2 plus is equal to 0.0483 times, I only need to worry about this guy because earlier it said is the only one reacting is that, and then times 0.01511. Let's figure out how many sig figs I need. I'm going to need to do this to 4 sig figs. Oh no, 3 sig figs. So then, equal to that. 0.0483 times 0.01511. 0.043, 0.041 is 7.298. 981 times 10 to the negative 4 moles. So then the number of C10, H14, and 2 is going to be equal to half the number of CH3, COOH plus equal to 0.5 times 7.298, 2981 times 10 to the negative 4, which is 3.6491 times 10 to the negative 4 moles. So you find the molar mass of C10. Actually, wait, no. So this is in, I'll say in 20 milliliters. Resulting solution. So the number of C10, H14, and 2. I'll say diluted factor. Oh no. No, because it's not diluted at all. So in 100 milliliters is equal to 5 times that. 5 times 3.6491 times 10 to the negative 4. 3.6491 times to the negative 4. 1.8246 times 10 to the negative 3 moles. So then let's find the molar mass of C10, H14, and 2 equal to 10 times 12.01 plus 14 times 1.008 plus 2 times 14.01. That's right, this is a bit of an odd titration. Using acid to form that. Interesting. Anyway, what have I done? I was doing this 10 times 12.01 plus 14 times 1.08 plus 12, also 2 times 14.01. So 162.232 grams per mole. So then the mass of C10, H14, and 2, and this is in 14 packets. 14 packets is equal to 162.232. This 2 is a bit odd. 62.232 times 1.8246 times 10 to the negative 3 is 1.8246 times 10 to the negative 3 is 0.29601 grams. So then the mass of C10, H14, and 2 in one packet is equal to 0.29601 all over 14. 29601 by 14 is 0.0211 grams is equal to times 1000 should be 21.1 grams. Therefore, it's 21.1 dosage per pouch. Dosage per patch is 21.1 milligrams. To identify nicotine dosage per patch in the unlabeled boxes. Dosage per patch. Let's label box as patches. Okay, because I'm not sure if they want me to say dosage per patch is this, or if I should go from the ones listed, which is only 21. So I'm just going to do both, shotgun method, and I'll definitely get the mark. Glycol. What is this called? Empirical formula. Carbon, hydrogen, nitrogen, oxygen. Task determining empirical formula and molecular formula. Gel method determine the nitrogen content of another 2.3 grams. We're converting all of the nitrogen atoms in the sample into ammonia. With the ammonia then distilled into that, which will excess reaction between ammonia to excess sulfuric acid. And 15 to complete the reaction. What the heck is happening? Okay, so let's just find number of carbon. So number of CO2, which is 2.84. 2.85, yeah, 5. 44.01, which is 0.6476 moles. So then the mass of carbon is equal to 0.06476 times 12.01 times 0.06476. 1, 2, 3. That is. Yeah, that's correct. Okay. And the number of hydrogens. 2 number of H2O. 2 times 0.874 all over 18.016. Which is 0.09702 moles. And the mass of hydrogen is equal to 0.9702 times 1.008. 2 times 1.008, which is 0.0977980 grams. Okay. So to complete the reaction, so number of NaOH is equal to, so I'm gonna have the number of NaOH, and then I can find the number of H2SO4 left over, and then since I have the H2SO4 left over, I can find how much of it reacted from the total. The number of NaOH is 0.0154 times 0.186. 0.154, that's right, 186. Should equal to 0.028644 moles. Number of H2SO4 excess is equal to half number of NaOH is going to be equal to 0.0014322 moles. And then the number of H2SO4 total initial is equal to 0.025 and 1.35 times 1.35, which is 0.03375 moles. Therefore, number of H2SO4 reacted is 0.03375 minus 0.0014322, and this will give me how much reacted, how many moles reacted. So 32318 moles reacted. So then my number of nitrogens is going to be equal to 2 times the number of H2SO4 reacted, which is going to be equal to, bring this all the way back up, because I have 2 nitrogens, H2SO4. I'm going to do 2 times NH. Number of nitrogens is equal to my number of ammonia, which is going to be equal to 2 times the H2SO4 from my stoichiometric ratios. So then now we'll bring this all the way back up. Which is equal to 2 times 0.032318. 32318. 323 times 2 which is 0.0646636 moles. So then my mass of nitrogen is going to be equal to times 14.01 0.0646636 0.90555 grams. So my mass of oxygen is going to be equal to 2.3 0.9055 minus 0.7777 57, so I need an extra 5. Minus 0.0978. 0.0518 grams. Wait, no. 51888 grams. So the number of oxygens is over 16, which is 0.03243 moles. So number of oxygens is least. Therefore, number of nitrogen over number of oxygen, this should just be 2. 64636 divided by answer, yes, 2. Number of carbons over number of oxygens. Carbons is 0.06476. 03243. It's also 2. And the number of hydrogens over the number of oxygens. 9702 by 0.03243 should be 3. Therefore, empirical formula is going to be C2H3 N2O. Very interesting. Okay, another was vaporized as that. The total volume was that. Determine the molecular formula of glycerol. So M of C2H3 N2O is 2 times 12.01 plus 3 times 1.008 plus 2 times 14.01 plus 16. Alright, plus 2 times 14.01 plus 16. 71.064 grams per mole. So the number of glycorial is going to be equal to PV over RT. So pressure is 242 times volume, which is 0.663 or 633. Over R, which is 8.314, times T, which is 273.15, plus 865. This is going to give me 314 plus 865. 0.01619 moles. So the molar mass of glycol equal to 2.3 over 0.01619, which is 142.063 grams per mole, which is equal to about twice the molar mass of my C2H3O2N. Wait, no, N2O. What's N2O, right? Yes. And for molecular formula, it's going to be C4H6N4O2. I was going to put approximately, but now I'll leave it. How many pages were there again? Was it 38? Okay, so I have 8 more pages to go. Okay, a chemist was asked to develop a method of recycling used cathodes from a new lithium battery. The cathodes were a mixture of lithium cobalt oxide and magnesium. Preliminary trials showed that the used cathodes would dissolve completely if enough sulfuric acid and if enough time was allowed. The chemists decided to conduct detailed trials to show how sulfuric acid concentration affects the rate at which the used cathodes dissolve. Each trial was performed in a sealed oxygen-free reactor using 5 liters of sulfuric acid and 0.531 kilograms of each cathode. Trials were also performed in the presence of Fe2+ ions to see if these ions had a catalytic effect. All trials lasted for 15 minutes, with the reactor solutions then analyzed with the concentrations of that. The results of the CO analysis are shown below. Which trial numbers will allow chemists to determine the relationship between the sulfuric acid concentration and the amount of cobalt extracted? So 1, 2, 4, and 5. Because you can't be changing the other things. So 1, 2, 4, 5. 1, 2, 4, and 5. The effective acid concentration on the rate at which the used cathodes dissolve. As H2SO4 added. Maybe aqueous is added. Concentration of H2SO4 increase. Therefore, the frequency of reactant collisions increase. Frequency of reactant collisions increase. Therefore, reaction rate of forward reaction, which is the dissolving of cathode, will also increase. How is this 3 marks? Reaction rate of forward reaction will increase, therefore dissolving of cathodes rate. Let's say increased number of reactive particles per unit of volume. Frequency of reactions. FEs catalyze the solution of cobalt and sulfuric acid. Yes. With H2SO4, with only 8.8 molar H2SO4, CO2 plus is 6.96. 6.96 times 10 to the negative 1 molar after 15 minutes. But with 8.8 molar H2SO4, and because you need to compare it to something where it's the same number of H2SO4. So I can't use this one because there's no other trials that just use 5.91. So we'll say, but with 6.62 times 10 to the negative 1. Fe2 plus. The concentration of CO2 plus is equal to 9.95 times 10 to the negative 1 moles after 15 minutes, indicating reaction rate had increased. Increase reaction rate has increased to allow for faster formation, for faster solving of CO. the solution. But I also need to talk about how it's not consumed. Also, concentration at Fe2 plus before. And after are nearly identical, indicating it wasn't consumed in the reaction, just like catalyst shouldn't. Just like a catalyst shouldn't. Hence, Fe2 plus catalyzes the reaction. Okay, what the cathodes is all completely in trial 2, assuming there's enough time allowed to support your answer relevant calculations. Okay. So in trial number 2. So my number of H plus is going to be double. Number of H plus is going to be double my number of H2SO4, which is going to be equal to, my god, the iPad is getting laggy now, 3.01 times 5, which I'm just getting from this table. I'm just reading this value for the concentration, and then it says we use 5 liters. So then here is 15.05 moles. Oh wait, I need this times 2. So this is actually, so it's 10 to 30.1 moles. So then we'll say number of ICO2 max. So it's going to be equal to quarter number of H plus, which is going to be equal to 30.1 divided by 4, which is 7.525 moles. So then let's say so we know we have that and then that. So the mass of cobalt is CO 0.531 times is 52.29, so 0.52729, which is 0.3042 moles. For oh wait, no, this is grams. This is the mass. So this is grams. 5729. 0.531, 5729. Number of cobalt is equal to, and so cobalt is 50.93. So 0.3042, 58.93 Why this is gonna be so far off? I'm missing something. Lithium carbide oxide. All my cathodes are completely in trial 2. It's 3.01. And we use 5 liters of sulfuric acid. So there is a lot of H2SO4. Oh, kilograms. This is kilograms, so I need to multiply this by 1,000. There we go. That was what was wrong. So 531 times 0.5729. 304.21 grams. There you go. Now this will be like what? 6 moles or something. 304.21 all over 58.93. 304.21 divided by 58.93. 5.1622 moles. So then the number of LiCO2 actual has to equal the number of cobalt moles as the number of lithium cobalt oxides actual. Oh man, this is what happens when it's super laggy and I don't get immediate feedback. And when I'm writing, I write 2 O's. CO02 actual is less than lithium oxide max dissolve. Then given enough time, the used cathodes will dissolve completely. Would solve completely. I think that's it. Okay, page 30 here. Calculate the percentage by mass of lithium in a used cathode. Give your answer to the appropriate number of significant figures. Lithium in a used cathode. The number of lithium must equal the number of LiCO2 can be equal to 0. I should write this as an O. 51622 moles. So the mass of the lithium can be equal to 5.1622 times 6.94. So 35.83 grams. Appropriate number of significant figures. I'll just do it to 3 then. I just do it by I do it to 3 because of this. So 531. Therefore, percentage mass lithium. Oh my god. So equal to 35.83 all over 513. Or was it 531? 531. Did I do 531 down here? Okay, I did 531 minus 100. 100 is going to be 6.75%. 34. So ferric acid is manufactured by the contact oh no, oh no, oh no. Reaction equations. Oh yikes, man. Okay, I think I'm gonna have a quick toilet break before I start this question, and then I'll be back. So, pause. Okay, with that, what was supposed to be a quick toilet break ended up being me going for something to eat and helping my dad with cleaning around the house. So it's now like 4 hours later or something. So we are ready to continue going, so let's go. Use our understanding coding theory and chemical equilibrium to discuss reaction condition for step 1 and 2 of the contact process. Produce the greatest yield in the shortest time. So let's just talk about step 1. You could say as. Oh wait, hold on. Pause. Gotta put my timers up. And we're back. Step 1. Say as temp increase, average kinetic energy particles increase, velocity of particles therefore frequency of collisions increase, also proportion of minimum activation energy will increase, therefore more successful collisions will result in reaction, therefore so these two factors cause reaction rate to increase. Therefore, temp as high, no effect on yield, as not reversible. As high as possible. So high temp of 1000 used. Higher temperature not used for, as it would be a higher temp it would require more expensive machinery and be more expensive to run. Okay, so then step 2, we have a lot to talk about. Step 2. As increase, reaction rate would increase due to increased frequency of collisions and increased proportion of particles with minimum activation energy. Ah, you're kidding me. How much got removed? Okay. Pause, I'm gonna rewrite everything and then we'll be back. I've wrote everything. I think to step 1, I'm gonna add something here. So it's more expensive to run, it requires more expensive machinery and extra reaction rate gain is insufficient to compensate for extra loss. Oh, not extra loss, for extra cost. Not sure if that'll be part of the map, but you know, whatever. So then as temperature increase, reaction rate to increase, however. As temp increase, LCP, the endothermic reaction is favored. Proposed change by absorbing the energy to lower temp as written. Reverse reaction is endothermic. Thermic, therefore, as temp increase, concentration of, say, reverse reaction favored. Action favored. Therefore, concentration of products decrease. So then the SO2, SO3 required. SO3 will decrease, and for my yield will decrease. So I'll say thus, as temp increase, increase, but yield will decrease. A moderate temp of 450 is used. A moderate compromise. And then we have pressure. So as pressure increase, concentration of gaseous species, concentration of gaseous species increase, therefore increase frequency of collisions, therefore increase reaction rate. Of both forward and reverse. Reaction rate of both forward and reverse. Kinetic energy, reaction rate increase of forward and reverse. And then let's see, when pressure increases, we're going to want to go to the right, increase the 10. So then also as gaseous molecule ratio, I always write ratio. Ratio is 3 to 2. As pressure increase, forward reaction favored, say by OCP, forward reaction favored to decrease pressure, to oppose change, and therefore concentration at SO3 will increase, for yield increase. Then I think that they don't do it at too high temperature, otherwise otherwise the pressure, too high pressure, otherwise the temperature will increase too much too fast. And it says here economic concerns. However, due to reaction being exothermic, pressure is compromised to moderate to relatively low, also industrially low, relatively low slash moderate of 100 to 200 kPa. To ensure temp doesn't rise too high, otherwise would require more costly equipment. To maintain. And then we can also say adding catalyst, adding a V2O5, increases reaction rate of forward and reverse. Plus reactions. As it introduces alternative reaction pathway with lower activation energy therefore more particles can successfully react. Create a proportion of particles. With the lower minimum energy. This allows for milder this allows for acceptable reaction rate at milder temp and pressure conditions. Reducing energy and complexity of system, therefore reducing costs. Okay, page 36. The oil extracted from the seed of a particular tree containing the presence of triglyceride means that this oil can be used to make ethyl paramylite, a type of biodiesel. The condensed structure formula of ethyl came below. How ethyl can be synthesized from that. The synthesis method must use ethene and lipase. You can also use water and any other laboratory acids. Use condensed structure formulas to represent organic compounds. State symbols are only required for inorganic substances. So use condensed structure formulae to represent organic compounds. So ethene, which is CH2CH2 form plus H2O. H2O liquid. And we're going to have a lipase there. No, this is going to be fermentation. Ethyl can be synthesized from that. The synthesis method must use ethene and lipase. You can also use water and any common laboratory acids. Lipase is to okay. So lipase is going to be for the formation of the actual biodiesel itself, not this. Here I'm just going to have H2SO4 aqueous. That's my catalyst. So there's going to be CH3CH2OH. Balance reaction equations. Ethyl paramylite to synthesize must use ethene and lipase. So this is going to be my, it's probably going to be gaseous, H2SO4. That's my catalyst, and then I'm going to make ethanol. And from here, ethanol, oh, that's going to be double arrow. And from here, CH3, CH2OH plus this CO, CH3, So then H2C, HC, H2C, and then OOCH, CH2, 14C3, OOC, CH2, 14, CH3, OOC, CH2, 14, CH3, this is going to form lipase. So I have this and lipase, which is then going to make the H2 COH, HCOH, and then H2COH, glycerol, plus 3 H2, oh no, CH3, CH2 14, COO, CH2, CH3. I think that's it. Ethyl can be synthesized from that. Ethene, which is there. Lipase, which is my catalyst. Any other common laboratory acids? Stain symbols are only required for inorganic substances. I think this is so good. Series of balanced reaction equations. I don't need two there, because then I just make my ethanol, and then I react to ethanol, which is an alcohol with a triglyceride. Presence of the perfect catalyst, which is going to be that. So I think that's it. The chemist investigated the synthesis step involving lipase, referred to in part A. The results obtained by the chemist are shown below. Construct a question that the chemist might be trying to answer in this investigation. What is the optimal temperature of the reaction system to maximize yield? The optimal reaction system temperature to maximize the biodiesel yield. Graph the data on the following grid. So I'll say temperature, degrees Celsius, temperature reaction, temperature reaction system, and degrees Celsius. Again, it's biodiesel yield of 20%. Okay. Then we're going from 20 to 60. So I could probably just do this in 10 intervals. 2, 3, 4, 5, 6. Ooh. 5 intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, nice. So I'll do 5-degree intervals. Here I do 5, 15, 20, 25, 30, 35, 35, 40, 45, 50, 55, 60, 65, 70. And here I'll do yield, which is 65 to 75. So maybe I'll do something like this. And I'll do like 60, 65, 70, 75, 80, 85, 90, 95. 60, 65, 70, 75, 80, 85, 90, 95, 100. So then at 20 degrees, we are at 65%. So boom, at 30 degrees, we are at 78%. 78 here. 76, 77, 78, 79. 1, 2, 3, 4, 5. And then 35, we are at 85 degrees here. At 40, we are at 88. So there. At 50, we are at 91. 50 is 91. At 55, we are at 92. At 60, we are at 85. And then at 65, we're at 75%. So then this can be called biodiesel yield percent across varying action system temperatures. And then I'm gonna have to draw like a line of best fit, and this one has to be a curved one. So like this, maximum there. Something like that. And I'll just label this line of best fit. So then describe the relationship observed in the graph. Parabolic relationship. Oh, what would you call this relationship? Is it just non-linear? Non-linear parabolic relationship between biodiesel percent nonlinear inverse parabolic and reaction system temp. Explain how the use of lipase in the synthesis contributes to the relationship described in part D. So then lipase is temperature sensitive. I dot E, there is an optimal temp range where it will operate. And beyond that, temp range, its function severely decreases, is severely hampered, leading to decreased reaction rate, therefore decrease biodiesel. Beyond that and below it. So beyond and below, the optimal temp range is function severely hampered, leading to decreased yield of biodiesel. Operate most effectively. Lipase, like all enzymes, is temperature sensitive. An optimal temp range max yield at around, what is that, like 45 to 55, around 50 to 55, around 50 to 55 degrees Celsius. Say here, likely 50 to 55 degrees Celsius, where it would operate. And below, its function is severely hampered, leading to decreased yield of biodiesel. Its function is severely hampered due to breaking down of its structure. Describe the relationship observed in the graph. Inverse parabolic relationship. I don't think that's a nice explanation. Oh well. Okay, I'm gonna end it here and I'm gonna mark. So I'll see you guys in like a second for you, but like probably about an hour for me. Just marked it. While I was marking, I have been informed that I can't use shorthand like arrows or 3 dots when explaining. So I'll do that for next exam, because I mean, if I mark it like that for this exam, I'm gonna get like 20%, because every one of my answers pretty much has an arrow or 3 dots. So I'll have to keep that in mind for next exam. But we have improved again, which is very nice. 94%, we're getting up there, guys. Again, we lost 2 in section 1. Only lost 1 mark in section 2, which was quite good. And then we lost 8 in section 3. So going through them, first mark we lost was this one, because secondary cells, they are rechargeable, but the Lalande cell is not an example of a secondary cell. A secondary cell would be something like the lead acid accumulator. So the correct answer was A, because primary cells are not rechargeable, and for example the Lalande cell. So we lost 1 mark there, and we lost another mark. I believe it was this one. I don't know. Ocean acidification, weaker building of seashells. I'm not sure where else you can go with this, so I guess I got that wrong. I remember I was discussing this question, and someone said because when you increase the concentration of CO2 aqueous, this will go to the left, which is actually like opposing what 5 is saying. So yeah, it does not, because it would lead to increased building or stronger cells or stronger shells. But I don't know, because it talks about acidification, not the release of CO2 into the atmosphere and into the ocean. But whatever. So yeah, all of these, the rest of them were fine. Here, we did good. For this question, you could have just circled that C, and you could have said that carbon contains 4 bonds, which is, yeah. And for this one, you could have just said oxygen contains or needs 2 single bonds. And obviously here there's only 1. I thought me covering that it either needs to be connected with a hydrogen or have a double bond to the carbon. It's the same thing, because then you get 2 bonds in either way. So I gave myself the mark. This was all good. Here, I did the ionic too far, ionic equation. I should have just left the Mn there, because that MnO4 is not going to dissociate. So I should have just left it here, so I knocked 1 mark off, but otherwise it was all correct. Down. Let's go. Oh yeah, here I said prevent significant changes, but pH says resist. And then for this, it had a straight arrow, but then it wouldn't be a buffer equation. So this equation was in the marking key, just that the arrow was straight, which doesn't make sense, to me at least. So I decided to give myself the mark. Maybe I shouldn't have, maybe I should have, but yeah. Because I checked Pearson. Pearson does double arrows for all of the different buffer equations, and then if it doesn't have the double arrows, then it's not a buffer equation. If that makes sense. So yeah, like, because then if I add H plus to this and it's only single arrow, it doesn't explain why it can prevent me adding acids, because with a double arrow I can say that this goes down, so it goes to the left, but without the double arrow I can't say that. So I'm going to give myself full marks there. So a total of 6 marks. This was fine. This was also well done. This was good. This question here was quite easy. You could have just said here not at standard, and then here not at standard, whatever it is, standard conditions. But I said since it's not at 25 degrees Celsius or not at 100 kilopascals, then I gave myself the mark. Actually, wait. Is the pressure at 100 kilopascals for standard conditions of an electrochemical cell? Predicting direct. Okay, hold on. I'm using Pearson right now. So 1 molar concentrations and 100 kilopascals at 25 degrees Celsius. So yeah, it's not 100 kilopascals, so I give myself the mark there. And I'll just follow along with the marking key. Question 30. Here we go. We'll continue down. Again, some basic redox reactions, pretty easy. For this, you didn't even need to say that. You could have just said the oxidation numbers changing. And here, this was a bit wishy-washy if I should get the mark. The marking key said that all you needed to say was that the E0 of Mg was less than the E0 of the Fe. But I think with this explanation, was also worth a mark, because I said, therefore it's more reactive, so then we'll get preferentially oxidized, which is what a sacrificial anode needs to happen, rather than just saying it's negative or more negative. So I gave myself the mark. Down. The diagram was good, very nicely done. I think on the marking key it didn't even say this. Ooh, wait, hold on. I didn't actually draw back the delta H. No. Change in enthalpy is labeled. Ooh, didn't I draw this here before? Oh, I must have drew it, and then I needed more space here, so I erased it and then didn't put it back. Do I knock his mark off? Do I knock a mark off? Oh, I feel like I might have to knock a mark off. Do I knock a mark off? Do I knock a mark off? Do I say? Well, I guess, I mean, I didn't do it, so I guess, yeah, knock a mark off. Alright. Well, I guess I lost an extra mark. Oh, that was so silly. Can't believe I've done that. So that'll be 5 marks for this page. So I'll change this to 74. Change this to 74. And then so our total is now 93.5%. Yikes, that's kind of embarrassing. Alright. I forgot to label it. Well, it's not that I forgot to label it. I did label it and I got rid of it. And I must have thought I had it still. But yeah, okay. So, lost a mark there. Yeah, everything was pretty much just like the marking here, except that it said the concentration specifically of NH3, and then NH2 and N2, or H2 and then N2. And then like here, apparently I'm not allowed to use arrows anymore, or the dot or the triple. I have to write hence. Like, oh my god. It's just a waste of time. I don't understand why I have to write increase decrease. It's an arrow going down is pretty ambiguous when I have it right next to product. Even if you say product going up, that the concentration of product going up does the same thing as product increasing. Like, I don't understand. What else could an arrow stand for? Going upwards? So increasing? God. Okay. And then my diagram was good. Down here, it was pretty good. Instead of saying the sum of the attractive IMF, they only talked about dispersion forces because it's the primary one of Deccan 1.0. Dispersion forces specifically between Deccan 1.0 and water. So yeah. Okay, so I lost 1 mark there. And then I lost another mark. Where was the another mark I lost? Oh yes, here for my ionic equation. Okay, on to section 3. This was fine, just really annoying to draw. Cysteine, these 1 markers were really easy to do. Yeah. So 2 differences. More differences you could have said was that the condensation forms polyamide / esters and addition does not. And then addition polymers have the same empirical formula as their monomers, which condensation does not. So going down. And then, oh yeah, the ones that I said were fine as well. So let's see what question is this. What are we up to? 34. Question 34. So all of the ones you could have said is condensation polymerization produces small molecules such as water. So yeah, I said produces water while addition does not. You could have said addition polymerization involves conversion of a C double bond to a single bond. Condensation does not. You could have said, I've said that one. Condensation polymers involves the reaction of monomers with different functional groups to form bonds in the polymers. Requires polymers with different reactive functional groups. And then has the same empirical formula, so yeah. And then going down, this was all fine. This was all fine. Here, this wasn't exactly one, I guess, because it was so vague. But there was one that says does not react with CO2 from the atmosphere, or low reactivity with CO2 or O2. So I give myself the mark there. You could have also said stuff like highly soluble. Could have said stuff like the no impurity one, not deliquescent or hygroscopic, not deliquescent or hygroscopic. Predictable reactivity, which is kind of what I said, I guess. And then yeah, and then going down, that was fine. This is good, 20 milligrams, blah blah blah, blah 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 blah. Here's where we start to lose some of the marks. We lost 1 mark here because the marking key said H plus. The higher the H plus concentrations. I didn't say that. I just said H2 SO4 concentrations would increase. I guess H2SO4 will fully dissociate. So I should talk about H plus, so I knocked the mark there. Someone pointed that out. And go down. It was fine. Here I lost the mark because I misinterpreted the what do you call it? The equation. What you actually needed to do was find the number of moles of the manganese and then show that it's a limiting reactant for the lithium cobalt oxide instead of doing it with the H plus aqueous ions. So I went the H plus route, so I got the marks up to, let me find it, up to my number of cobalts. So I got my marks up to there. But then the rest, everything below that was wrong. So yeah, it wasn't limiting reactants of this, it was limiting reactants of this, which is a bit odd because how am I supposed to know which one it's supposed to be? So then going down, this was fine. Here there was a mark, okay, this was weird because there was 7 dot points but only 6 marks allocated. But there was a mark allocated, well, no, it was split up into rates, equilibrium, economics, and then compromises. And in the rate section, there was 7 dot points, but 6 marks. And one of the dot points was that it's a combustion reaction, so it essentially goes to completion at high temps. But I thought it's one of the dot points. I didn't talk about it, so I'll knock a mark off. But everything else was perfectly fine. Except for the fact that I used arrows, which apparently chemistry markers don't know what they are, or the fact that they don't know what 3 dots are. I mean, like, they might as well tell me to not use like apostrophes. They might as well tell me to not use apostrophes here if they don't know what that means. Bro, how do you not know what an upward arrow means? How are you going to be marking these exams, and not know what an arrow means? God's sake. And then going down, it was actually quite good. The equation, they should have a forward arrow, but there wasn't marks allocated to arrows. And I'm pretty sure, I checked in Pearson, the creation of this alcohol is a reversible reaction, so it's fine. H2 in a gaseous state. And then this equation was also fine. Everything's correct here. No different from the marking key for this one. It's always nice to see. You got 4 marks for each. You got 1 mark for each reactant, each product, 1 mark for each reaction being correctly balanced, and 1 mark for each catalyst. This was fine here. For this one I wasn't sure if this was a valid explanation, but for the bottom one was fine. I just skimmed the first mark because you had to say the lipase is an enzyme or a protein, and I said lipase like all enzymes. So I think it's close enough to give myself a mark because that quite strongly implies that lipase is an enzyme. And then here you have to talk about a yield steadily increasing as temperature increases, reaching a maximum at 55 degrees, and then the yield percentage decreasing at higher temps past 55 degrees Celsius. Now, an inverse parabolic relationship kind of implies that it goes up, reaches a maximum at 50 to 55 degrees Celsius, and then comes back down. So I'm not sure if I should knock the 2 marks off or if I should not. But I assumed it's nothing like the marking key. I didn't especially say that it goes up and it goes down. So I guess I'll knock the 2 marks off because I would have only got half of the first mark right, and I don't think half is worthy of a full mark. So yeah, that's 2 marks gone, 2 marks gone, 1 mark, that's 3 marks gone, that's 7 marks gone because I lost 4 there, and then 1 mark gone there. So it's 8 marks lost in total. Otherwise, we did pretty good. So yeah, revised total 93.5%. I gotta remember to not use arrows for my next exam and to not use therefore marks. So I think the next exam I'll do is probably a physics exam. And then I'll do 2 chemistries after that. And then by the time that rolls around, it'll be my chemistry exam. And then I'll start alternating between physics and methods. And then once I finish those exams, I will just do bang on like 6 days straight of specialist exams. So that's my plan for the next few days. See ya.